Hello, hello. We are back together again. And today we're talking about absolute and conditional convergence and the alternating series error bound. Well, what the heck are those? So far, we've been asking whether or not a series converges or diverges. But there's actually another layer that we can add to this question. If the series converges, does it converge absolutely or conditionally? All of what we've learned so far about convergence is now in play. So tee up all of those convergence and divergence tests in your head. Absolute convergence. If the absolute value of a sub n, the infinite series of that, converges, then its original series also converges. Conditional convergence. If the absolute value of a sub n, its series, diverges, but the original series, a sub n, converges. In other words, what we're asking here is, does a series only converge on the condition that it is alternating? Let me show you what this means. We've got a number of series here, and this first one, that's the harmonic series. It diverges. Now, when we add an alternatingness to it, we get the alternating harmonic series, and it converges. Huh. All right, let's look at this one. That's a p series. P equals 4, so that series converges. If we add an alternatingness to it, then we have an alternating p series with a p equals 4, and it also converges. So on the top here, we call this conditional convergence because the alternatingness here that we added made a divergent series convergent. But below here, absolute convergence, when we added alternatingness to it, nothing happened because it was already a convergent series. So let's determine if the following series converges absolutely, conditionally, or just plain old diverges. Now, this is an alternating series because we've got this negative number raised to the nth power. So if we want to take off the alternatingness of this series, we just take the absolute value of it. So we get 3 to the n over n factorial. So again, the absolute value negated the alternatingness of the series. Now, let's just look at this one. And like I said earlier, we've got to tee up all of our convergence tests that we know. And which test would we use to determine if 3 to the n over n factorial converges or diverges? I think the best one for this is going to be the ratio test. So I need to get my n plus 1 term divided by my n term. And we can clean that up a little bit and start canceling some stuff out. And the limit as n approaches infinity of 3 over n plus 1, that's 0, which is less than 1. So according to the ratio test, the 3 to the n over n factorial converges. When I took the alternatingness off, I still had a convergent series. So the original alternating series converges absolutely because it doesn't matter if it's alternating or not. Okay, let's try that again. We're going to take the absolute value of our series here, and we'll have 1 over n to the 1/3. Okay, so that's a p series, and it diverges because p is less than 1. So we need to look further. Let's go back to our alternating series, and we'll employ the alternating series test. We have an alternating series. Does the limit as n approaches infinity of a to the n equal 0? Yes, it does. Do we have a non-increasing function? We sure do. Our original alternating series converges, but it only converges conditionally because if we took off the fact that it alternates, it would diverge. Next one, take the absolute value and let's see what's going on here. We've got n over n plus 2. Which test would you use on this one? Let's start with the nth term test just to see what's going on. The limit as n approaches infinity of a to the n is 1. That diverges by the nth term test. So we're going to have to look further and go back to the alternating series test to see what happens with the original alternating function. So for the alternating series test, we, again, have to look at the limit as n approaches infinity of a sub n, which is still not 0. So this whole thing just diverges everywhere. Okay, now here's a new twist on it. Find the values of x that make the series converge absolutely. So if we want the series to converge absolutely, there's all kinds of stuff going on here. So let's use the ratio test, and we'll do the whole ratio test within absolute value brackets so that it's not alternating. And so this -1 to the n here is not really a factor anymore. So I've got my n plus 1 term divided by my n term. And in order for this to converge, I need this whole thing to be less than 1 because of the ratio test. So I can do some canceling here. And then once I've canceled, I'm going to clean it up and I'm going to put all the n terms together and all the x terms together because then I can really see what's going on. Now remember, as we're taking the limit, it's n that is going to infinity. X doesn't really have anything to do with it yet. So here are all my n terms. As n goes to infinity, what does this guy go to? It goes to 1. So now we can use this information to solve for x. We know that the absolute value of x plus 4 over 6 has to be less than 1. And now we just get to solve this inequality. So as long as x is between -10 and 2, this series converges absolutely. Let's try another one like that. What values of x make the series converge absolutely? Let's use the ratio test again. That's a good one. And we're going to do the entire ratio test within the absolute value brackets. So here again, we've got the n plus 1 term. We've got the n term, the reciprocal of the n term. And in order for this series to converge absolutely, this all has to be less than 1. So we'll do some canceling. We'll get the n terms together and the x terms together. And then we can actually take the limit as n approaches infinity. And that's going to go to 1. So we have the absolute value of x minus 1. That has to be less than 1. And we can solve our inequality. Anytime x is between 0 and 2, that series will converge absolutely. Now let's add another little layer here. Instead of wanting it to converge absolutely, what if we care about where it converges conditionally? We know that it converges absolutely between 0 and 2. In order to find where it converges conditionally, we need to check the endpoints of our interval into the original series. So I'm going to plug 0 in for x, clean this up a little bit, and this is, it's the alternating harmonic series, and I know that converges. So if x equals 0, the series converges conditionally. Now let's check the other endpoint. So now I'll plug in 2 for the x value, and I get just 1 over n. That's the harmonic series. It diverges. So the only place that this series converges conditionally is if x equals 0. alternating series error bound. We may not know exactly what a series converges to, but if we do a partial sum, how accurate would it be? Now, in this lesson, this part of the lesson, it's all about the next term. Let me say that again. It's all about the next term. I'll show you what that means. Here's Jim, and he's going to show us the alternating series error bound using the alternating harmonic series. So we're going to fill this table in. First, we're going to figure out each of the a sub n's, each of the terms for n equals 1, 2, 3, 4, and so on. Then we're going to take some partial sums below that. So first we'll start with the terms of the harmonic series. And if we put that into decimal form, that's going to help us a little bit later to see what's going on. Now let's take a series of partial sums. So the first partial sum is just the first term, that's 1. The second partial sum is the first 2 added together, that's 1/2. The third partial sum is 5/6, and we'll keep going. So the eighth partial sum is 533 over 840. Again, let's change that into some decimal approximations because that's going to help us see what's going on. Now in the next slide, I'm going to make a graph of a series of points, n s sub n. So n s sub n. Okay, so watch this. Look at, they're all getting close to something. And this alternating harmonic series actually converges to the natural log of 2, or 0.6931. Now you'll notice that each of these points, well, it's not on the line, is it? It's a distance from the line. And as we get further and further on in our partial sums, this distance gets smaller and smaller and smaller. So what I'm going to do right now is just figure out what each of these distances is. So I'll take the point, the s sub n, and find the distance to ln of 2. So I'm going to call each of those a remainder. So the first distance is 0.30685. And then the second distance, that's remainder 2, is 0.19314. And then I'm going to do that all the way through until remainder 8. So again, I've just found all of these distances. And notice, thankfully, they're getting smaller and smaller and smaller, as they should, because it's converging to something. Now, we're going to pull up the terms of the sequence that created the series. And I want you to focus on these decimal equivalents right here. So let's look at the first remainder of 0.30685. That is less than the absolute value of my second term, 0.5. Now let's look at the second remainder, 0.19314. That is less than the absolute value of the third term. And if we keep going, let's look at the third remainder, which is less than the absolute value of the fourth term. See where this is going? The seventh remainder is less than the absolute value of the eighth term. And these are also decreasing numbers. So we can get pretty accurate as we take more and more partial sums, but we can also know how far off our answer could be. So this is the alternating series bound. If you have an alternating series that converges, then the error from using the first n terms of the series to approximate the value of the series is less than or equal to the absolute value of the first unused term. So here is the alternating series error bound written in like mathematics speak. So let's start by defining each of these little pieces. S is the actual sum of the series. S sub n is a partial sum. R sub n is the remainder or error. Mathematically speaking, it's the absolute value of S minus S sub n. Those were the distances we were finding on that chart before. And then A sub n plus 1 is the first omitted term, and it's also the error bound. All that to say, this term right here, the absolute value of A sub n plus 1, that's the boundary or the worst case scenario of how far off your error is from the actual sum of the series. How close is your partial sum? Example 7. Determine the number of terms required to approximate the sum of the series. So I know I can't get to the sum of the series, but I want to get really close, and I want to get so close that I know that I'm within 1/1000th of the actual sum. So what I know is the remainder is less than or equal to the next term or the first unused term. And I want that to be less than 10 to the negative 3. Well, if my original series is 1 over n, then I need to make an n plus 1 term, which is going to be 1 over n plus 1. And I want that to be less than 1 over 1000. And now we just get to solve this inequality. So in order to get so close that your partial sum is within 1/1000th of the actual sum of the series, I need to have at least 999 terms. Example 8. We can find all different ways to ask these kinds of problems. If this series, so we have an alternating series of 1 over 5n plus 2, is approximated by the partial sum with 10 terms. We're going to have the 10th partial sum. What is the alternating series bound? It's all about the next term. So if we have 10 terms, we need the 11th term. So 1 over 5 times 11 plus 2 is 1 over 57. That's how far off the 10th partial sum is, or less, from the actual sum of the series. We won't be more than 1 over 57 off. Example 9. Approximate the sum of the series using the first 5 terms. Okay, so here's our series. And we can use the calculator for this using our summation. So go to Math 0 on the TI-84 and just plug in right there. Plug in the problem for the 5th partial sum. And we get 3.3544444. Okay. Now, that's only an approximation. But like, what might the actual sum of the series be? Well, we've used the first 5 terms added together. So let's check the 6th term. Remember, it's always about the next term. Well, the 6th term is 1 over 9, or 0.111111. So if I take my approximation and subtract 0.111 and add 0.111, then I know that the actual sum of the series is somewhere between 3.243 and 3.465. That's pretty nifty, isn't it? Example 10. Show that 1 minus 3 factorial approximates f of 1 with an error less than 0.01. With this whole series here. Wow, okay. Well, if we're working with an alternate series and we're curious about the error, then I know that the remainder is going to be less than or equal to the next term or the first unused term. F of 1 is the actual sum of the series. 1 minus 1 over 3 factorial is a partial sum. But which partial sum is it? Well, let's go back up here to the original problem, okay? And if we're worried about f of 1, that 1 is an x value. So for each of the x's up here, I'm going to plug in a 1. And look what I have right here. 1 minus 1 over 3 factorial. So this 1 minus 1 over 3 factorial is the second partial sum. All right, now, does that second partial sum have an error less than 0.01? Well, if that's the second partial sum, we need to check the third term, the next term, which is 1 over 5 factorial. 5 factorial is 120. So we've got 1 over 120, which indeed is less than 1 over 100, or 0.01. Yeah, that's a lot, isn't it? There's a lot to wrap your head around, but I know you can do it because you're awesome. I'll see you in the next video.